to introduce Professor Jens Chluba from the University of Manchester. So Jens is visiting us within the framework of Fundación Occident. So he will be here for 3 weeks until July 7th. He's having an office in the first corridor downstairs, so in the same office as Frederic. So if you want to interact with him, he will be here 3 weeks. Take the opportunity to discuss. Jens, well, we know for a long time. He did the PhD at Max Planck Institute with Assis Sunyaev at the time that both Carlos and I were postdoc there. After MPA, he was in US, in CETA for a couple of years, then Johns Hopkins Institute for 2 years, and then he moved to UK, first with a Royal Society Research Fellow at Cambridge, and then he moved to Manchester. And you're professor there since
good question. Yeah, it's 5 years, 6 years.
5 years ago. Okay, so he's an expert in radiative transfer, early universe physics, and particularly spectral distortions, which is the topic of the seminar today. So hope you enjoy it. Thanks for coming.
Yeah, thanks Alberto and Carlos, and then also Ricardo and Paco. I'm really happy to see many old friends from various stages of my career, and thanks for having me here and also supporting this from the foundation. Yeah, so today I'm going to try to talk to you about spectral distortions. This is actually the topic of my PhD thesis, but my PhD thesis was in 2005, and so that was already many years ago. And I think at that time, we haven't really understood or really seen that there's actually a potential for measuring these signals now. And we are now, 20 years essentially later, really in the stage where we can maybe look at these new signals from the early universe that can tell us about, things that are happening in stages that we can't otherwise observe. So this is really exciting, and I hope I can give you a little bit of that excitement during this talk. I love moving around, so I hope that the recording will still work, but I'm going to try to stick as close as possible here. Anyway, so obviously cosmology is about understanding the universe as a whole, studying the Big Bang, understanding where the fluctuations come from, what seeded the structures we see in the universe, how do things evolve, what is dark matter, what is dark energy, all those questions that we all, I think in some version have heard about and are excited about. And beyond doubt, the microwave background, the temperature map that here the Planck, satellite has produced is one of the key ingredients in understanding the universe. We have learned so much from studies of the anisotropies of the cosmic microwave background, the temperature anisotropies, the statistics of these fluctuations, the power spectra, analyzing them in conjunction with other cosmological probes. We have really learned a lot about cosmology just from this. And we are now in the era of precision cosmology, and we can look forward to so much more coming with, now the B modes being searched for, things like lensing effects being studied with the microwave background, large-scale structural probes, all the exciting. Yesterday, we saw the first pictures of the Vera Rubin Observatory. I mean, there's so much coming in terms of cosmological exploration, and still the CMB and the anisotropies of the CMB are playing a key role in this, right? So for my talk, I'm not going to talk about these anisotropies. Microwave background anisotropies, forget about them now. I'm thinking about the signal that looks like this, the microwave background monopole. So the flux, the average sky flux, no fluctuations in at least to leading order, no fluctuations in the universe. And we're really interested in what is the, average sky flux. So Kobe Firas, in the 90s or in the 80s, 90s has measured the sky flux and has shown that the average sky signal of the microwave background is that of a black body. Yeah. So here is the black body theoretical curve, and it actually covers the measurement points. So the error bars of the measurements are so small that they are covered by the thickness of this theoretical curve, because it's so precisely measured and proven that the average sky flux of the microwave background is that of a black body, with a temperature of 2.725 Kelvin. And in fact, one should stress that this is the first cosmological parameter, because it is a cosmological parameter that we always forget, that has been actually measured with extremely high precision, below 1% precision. And only now we have reached, in the angular scale of the sound horizon, we have reached a precision that is actually reaching this or even surpassing it a little bit. So this is one of the best measured parameters of our cosmology, and it has been measured essentially 30 years ago. Yeah. And spectral distortion science is about departures of the real average sky signal from that of a black body. Yeah. So there's these parameters, mu and y parameters, which are usually used to characterize departures from this black body spectrum. And that's what spectral distortion science is about. So let's talk about these two types of distortion signals. They come from the early seminal works of Zeldovich and Sunyaev, of course, on understanding how energy release processes or even other processes that are out of equilibrium affect essentially the microwave background spectrum. And one of them is also very familiar with, to us with the Sunyaev-Zeldovich effect, where you have the clusters of galaxies, hot gas, basically upscattering CMB photons, right? And that gives the so-called Y distortion. Here's this beautiful picture for the thermaless Z illustration that was done back in the early days of studying Sunyaev-Zeldovich effect. And it essentially is the black body spectrum comes in, and you have a small shift in the energy of the black body spectrum. All the photons get shifted just a little bit. That gives you the Y-type distortion. Scattering effects don't change the number of photons. You're just moving photons in energy. Yeah. Here, of course, exaggerated with a Y parameter of 0.15. We now know that clusters of galaxies have more like 10 to minus 4 as a Y parameter, but there is an equivalent in the early universe as well. When you have heating in the universe, you get a Y-type distortion from basically the hot electrons appearing. And early universe is of course a broad range. So there's the very early universe, the primordial universe, where the mu distortion, which I will talk about, comes from. But there's also the later universe, which is basically, in terms of cosmological times, something like 8,000 years after the Big Bang, or at a redshift of below 50,000. So for me, the late universe is actually starting at redshift 50,000. Obviously, people that are looking at galaxies are smiling very strong right now. Okay, so the Sunyaev-Zeldovich effect happens when you have energy release in the late stages of the universe, below 50,000. If you inject energy at earlier times, you get a mu-type distortion. And the reason is that mu-type distortion, again, we learned from kindergarten almost, that a black body has no chemical potential. And that's true, but if you're a non-black body, you can have indeed a non-zero chemical potential. So if you inject some energy, but you don't change the number of photons, then naturally, no matter how you redistribute photons, in whatever shape you bring them, they will not be having the black body relations in terms of the number of photons and the energy density of photons. If you started with a black body, you know that the temperature, number density is T to the 3, and T to the 4 gives you the energy density. If you now change the energy density, but not the number density, then the two temperatures that you would deduce from counting photons or measuring the energy would not be agreed. So that means there's another parameter, and that's the chemical potential. And this chemical potential, non-zero chemical potential, is precisely what is created when you have many interactions of photons with electrons. And here's another version of plotting these distortions, because here you could see very visually this, and here the mu distortion is the black solid thick curve labeled D, where you have like a deficit of photons at low frequencies and a little bit of an increment above the black body peak. So very similar, but when you plot actually the difference with respect to the black body, the equilibrium black body, then this is the shape of the distortion that you would get for a mu-type distortion, the blue line, and for a Y-type distortion, the black line. So the Y-type distortion has a null, no change in the intensity at 217 gigahertz. That's like the Sunyaev-Zeldovich effect in the non-relativistic regime. And the mu-type distortion has a null around 230, 227 gigahertz. That means you can actually observationally, in principle, distinguish them. And if you measure a mu-type distortion signal, then you know that that is a signal that comes from a high redshift universe, above redshift of 50,000, up to something like a redshift of a few million, which puts you really into the very early stages of the universe. And then I'm also plotting here the red curve. Anybody having a guess what full thermalization would mean? Or interactive. So if I inject energy, but I fully thermalize, I'm essentially shifting from one black body to another. And this is the curve that you would have to add to get perturbatively from one black body to another. So it's nothing else than the spectrum of the temperature anisotropies. It's just the derivative of the black body spectrum with respect to the temperature. Okay, so let's put this into the context of the history of the universe. This is the figure that I showed earlier. Things starting early on with the Big Bang, inflation, and then formation of particles, BBN, and then the recombination, which is the time when you see really the anisotropies become visible, and then all the fun stuff happening at late times. And when we do CMB anisotropy physics, we are interested in learning about inflation by studying the anisotropies in the primary CMB, but also the secondary CMB, and lensing E modes, lensing B modes, all these fun things. That is what the CMB anisotropy science is about. With spectral distortions, we're essentially probing the thermal history of the universe, so energy release processes and cosmic explosions, if you will, from a couple of months after the Big Bang to today, right? And I told you already that you get the Y and mu type distortions, and this means that with spectral distortions, you're essentially probing another dimension of cosmic evolution, where you can also peek into the pre-recombination universe with the mu type distortions, because they are happening in the high redshift universe. So the simple naive picture is that we have the early phases being just thermalization. Everything is perfectly thermalizing because things are so dense and hot, and interactions really erase any energy or any particle photon injection that you would be doing. But then a couple of months after the Big Bang, when you inject energy, you can't erase the signal anymore, and you will get initially a mu distortion when it's very high redshift injection, or at late times a Y distortion, where you can estimate actually the coefficients, the Y and mu parameter, by just looking at the energetics of the problem. You can ask how much energy relative to the CMB have you injected, and then you get these estimates, which are the famous estimates that Sunyaev and Zoldovich did in their early works on this topic. So this is the general classical picture, but we know now that things are much more interesting, in fact. So first of all, we can of course calculate these signals, and I will show you a calculation for any kind of energy release history and photon injection history. We can calculate these signals very accurately, very similar to what we can do with CMB anisotropies. But we also know that the transition between the mu and Y era is, of course, not a step function. It's not like at redshift 50,000, now I'm changing to a Y distortion when I'm below it, and I'm a mu distortion before. You have a gradual transition, and this transition has time-dependent new information that allows you to actually really understand physical processes in a more detailed way when you measure the spectrum in detail. And there's also the helium and hydrogen recombination era, which I will talk about. So this is just basically trying to convince you that we now can calculate these things very well. We have codes like Cosmotherm that basically solve the coupled problem of baryon temperature evolution, electron evolution, recombination process, and spectral distortion evolution. We can even do spectral distortion anisotropies. I decided not to put much of that into this talk, and I will briefly mention it at the end, but it's a whole another dimension which is actually in great synergy with spectral distortion, with CMB anisotropy measurements, because you can now look at maps of the sky and the spectrum in every pixel, essentially. But we include, of course, all the relevant thermalization processes, very accurately model the scattering processes and all this. This can be all done very, very nicely now with codes like Cosmotherm. And here I just want to show you a typical evolution. Where are the young? Yes, I promised there's a movie. It's not very entertaining, but so I'm going to show you here essentially the spectrum. What's happening? Oh, was it not? Oh yeah, sorry. I'm just okay. So what I'm showing you is the spectrum, the spectral distortion. In the upper panel, really the intensity departure from a black body. So like the Y distortion and mu distortion presentation that I did before. But I'm doing this now for a particle scenario where I'm decaying with a, where the effective redshift of the decay is something like 80,000, totally made up. But this is not a scenario that's ruled out by, for example, Virus or even other experiments. This is just a scenario to demonstrate how this would look like. And I'm in total injecting a total energy of 6 times 10 to minus 6. So again, this is like 10 times below the Virus limit. So no problem, we can do this, right? But we're allowed to do this. And I'm going to try to show you how the signal will evolve. In the lower panel, I'm showing the effective brightness temperature departure from a black body. So if you were a black body, this would be 0. Also here, you would have 0. But if you're having the departure, you see that there's deficit of photons here. There's a lower temperature at low frequencies as well, correspondingly. And here, there's an increment of photons. And correspondingly, you also get closer to the black body temperature of the real spectrum. Okay, so let me start the calculation in a second, but I just wanted to say these computational coordinates are just useful for the calculation. They are basically dimensionless invariant frequencies. And the maximum of black body is something like 160. And here is the real frequency today. So this is in the terahertz regime. This is a couple of 100 gigahertz regime. And then here we are already going to the tens of gigahertz regime. And this would be essentially radio emission. Yeah. So that's what we're looking at here. And CMB experiments, it's not very visible. They basically measure in this domain. Yeah. So the typical signal, the gain about information is coming from, the tens of gigahertz to several hundred gigahertz. Yes.
Sure.
That's a great question, and it goes. So this is the final signal that we would be measuring for this scenario. I will now evolve it towards that.
Okay.
At late times, you have the electrons cool below the photons, because at redshift 200 roughly, the electrons drop out of equilibrium with the photons, and that leads to free absorption at low frequencies, and that leads to this dip at low frequencies. And indeed, this leads even to an extraction of energy at high redshifts, because the electrons are basically wanting to cool faster, but the photons are saying no, so they have to give them energy so that they keep the same temperature, and that leads to a negative mu distortion, which is, by the way, what we're seeing at the beginning of the calculation, which has started at redshift 10 to the 7, so just after BBN. And you see this negative mu distortion here, as I was just explaining, from this cooling effect. Then we're going to the redshifts where we're coming closer to the injection, and you will see how the amplitude of the signal goes up very strongly around this time. But you overcome essentially this cooling process and create an energy release distortion, continuously create it, and you get this evolution of the signal in this way with these different stages of, scattering physics versus free and double Compton emission. So one of the important things is, if you want to erase the distortion, you can't just redistribute photons in energy. That won't do it, right? If you add energy, you need to also add photons in order to get a black body. And the production of photons is double Compton and Bremsstrahlung, which is all included. And that's one of the reasons why at low frequencies, at least early on, you always see that everything goes to a perfect black body, because free and double Compton are really efficient at low frequencies. So anyway, these calculations, this was real time, but it was even the movie makes it slow. It takes like 30 seconds nowadays to do these calculations. So it's not unfeasible to do, big grids of models and do emulation of this, and all that is what we're doing, of course. Okay, so Virus has not seen any distortions. Why am I even talking here? What's so interesting? These distortions are very small. This limits energy release processes to 6 times 10 to minus 5 delta rho over rho. We can't really perturb the energetics of the universe, at least after redshift of 2 million or so, by very much. Before, we could in principle inject a lot of energy. Indeed, BBN is one of those processes, because the electron-positron annulation leads to a lot of injection of energy into the CMB. The neutrinos are out of equilibrium with that. That's why you have the difference between the temperatures. But that's all thermalized perfectly. At late times, we can't do much, because otherwise you would violate those bounds by Virus, which is extremely interesting in terms of constraints on cosmology. So, but why am I talking about this? The reason is because we can now, this is a busy slide, we can now hope to get much more sensitivity than Virus, and we might be opening windows to processes that should be there and that also could be there to constrain these different processes. And so here's a slide just showing basically redshift. So this is the label of, full thermalization, mu distortions, the transition between mu and y, and the y distortion late universe. And then you can think of this vertical axis just as signal strength, right? Virus was able to look at signals, let's say up here, so didn't see anything, right? Trivially speaking. But there is processes like the late universe, like structure formation, galaxy clusters, Sunyaev-Serlovich effect, that should lead to energy release that we will actually see in the average spectrum. Yeah. And then there's other things. In fact, all of those that are labeled in yellow are standard lambda CDM signals. So we will see the dissipation of acoustic modes, and we can see the recombination lines. I will talk about this and also the recombination lines a bit in the rest of the talk. And then there's also the adiabatic cooling, which I alluded to, but it is a small and very, very clearly modelable distortion, which just depends on the baryon density. Yeah. But the cool thing is that there's all this, discovery space here, which we can explore, and which links to many of those things that theorists, at least, are very excited about. So, for example, primordial black holes, decaying particles I mentioned already, dark photons, axions, annihilation processes, cosmic magnetic fields, cosmic strings, enhanced small-scale power. All these are things that various experiments are trying to constrain, and spectral distortions will help with this. And it will help with this in a really interesting way, because it will be able to say if these processes are happening at very early times in the primordial universe, in the very early stages of the universe, right? So that's exciting. And because we have lambda CDM distortions, which are all summarized here, we have targets that we can design our experiments for. We don't have to just say, oh yeah, there might be a distortion. No, there is distortions, 100% guaranteed distortions, which are these. Some of them are a little bit uncertain, like the Y-type distortion from late time universe, because the feedback processes and things like that can change the signal, but the distortion should be there. So we can learn about feedback processes and things like that. So just because I didn't mention, this is again the distortion, but I'm now showing logarithmic scales. So it's the absolute value. This is the negative branch of the Y distortion, right? The dip, and then the 217 null, and then the positive part of the Y distortion, just the intensity spectrum, right? What I showed before, but here in logarithmic units. And then we have the mu distortion from the dissipation of acoustic modes, which is this red signal, which is, already a small signal. It's a mu distortion at the level of 2 × 10⁻⁸. So energy release was of order 10⁻⁸ only, yeah, relative to the CMB. But that is a signal that is guaranteed also from the lambda CDM universe, and I will explain why that's so interesting in a bit. I didn't mention the relativistic correction to the late time universe signal, because clusters of galaxies, they are actually pretty hot. There's like electrons of keV, several keV in there. So they lead to a comptonization correction that actually changes the classical Y-type distortion, and gives information about the real temperature of the universe as well. So together, these two signals, the violet and this, is basically the late time universe signal, and it probes the total pressure of the universe, or total baryon density of the universe, as well as feedback processes and the temperature of the universe. So this is really an interesting observable. And then there's the beautiful recombination lines coming from the redshift 1000 universe, redshifted to us, and I will mention that again in the later part of the talk. So these are guaranteed signals. We're not making them up. These can be calculated even very precisely, definitely given a specific model, and we can look for them, which is a really cool thing. And that's one of the reasons why there was actually quite some activity in the past decades now on this topic. We're still in the, observationally, the best limits still come from Coviphyros 30 years ago. I was updating the slide, of course, all the years that I was talking about it. And there were stages where I could say 20 years ago, and then 25 years ago, and now it's 30 years ago, indeed. But it's really great to see that there have been many, many mission proposals discussed that can in principle improve the limits of Phyros by a factor of 1,000. So this is really exciting and really positive. Of course, it is still, an effort to get a real funded mission. And we have really great activities now, some of them from the ground. And you all know about TMS here with which Alberto is doing. And I'm really excited to be shown the latest, components of the detectors and everything. Then there's Cosmo, which Bruno Paolo de Bernardes just announced at the CMB 60 meeting, that Cosmo now has funding to be deployed to Dome C and actually start its measurements, at least for some part of the time, which is really great. There's also Apsara, an activity in India at the Raman Research Institute that Mayuri Rao is leading. And that is targeting the recombination lines at some few gigahertz frequencies, absolute measurements. And then Bizou, is the space is a balloon experiment that Bruno Maffei is leading. That was basically since last year is now in the phase A study, which means there's a positive, there's a high hope that it will actually be flying within, let's say, 4 or 5 years from now. So this is all not fiction anymore. This is actually happening, and this will lead to improved measurements at the level of a factor of 20 or 30 over Firas, which is already a major step forward, right? That is already in itself a transformational measurement in terms of like really being able to push the frontier. And with the space mission, which we have been talking about, we could in principle go even farther. There's one experiment that I wanted to highlight because also you guys probably know Ian Brown and Peter Wilkinson. It's called LBAS, which is a measurement at 1.4 gigahertz. And it's a measurement that we can actually do from Manchester. Here's the experiment setup, and they are currently working on some of the systematic effects and trying to understand the instrument. But this is another measurement that will be an absolute measurement. It's not going to fly in a balloon. I just didn't have any space here, so it's a ground-based measurement, of course. So we have real activity from the ground, and we have also, and some of you are directly involved, the M8 mission proposal that is currently under consideration for the ESA MCall earlier this year. So there's lots of hope to see some real progress in the next 10 years from the ground and balloon, and potentially maybe in the next 20 years, if we're lucky, we will even see that we have a chance to fly a space mission to maybe do really, really high significant improvements over Firas. So this opens a lot of really great science. And I want to highlight that ESA has actually recognized spectral distortions in their Voyage 2050 study as one of the important early universe probes of the early universe, and basically as a contender for an L-class mission in at least in the recommendation. Although we are currently considering that an M-class version might actually be really what we want to do on a timescale that's a little bit shorter, but that is actually really commensurate with a lot of the activities that we're also seeing with gravitational waves and pulsar timing and all this exciting stuff that JWST and all the observatories are doing. So we will do a lot of science with an M-class mission, and that's why we're currently pushing that. So anyway, this is really, I think, very exciting perspective and hopeful, a lot of hope. And let me talk now a little bit more about the physics. These were just statements to just highlight BIZU and TMS and all these activities on the ground are, of course, extremely crucial in this process. And I'm really excited that that's going forward. And I think there's lots of involvement needed, even more help with all kind of aspects of the analysis, foreground modeling, and so on, which are very, very clear problems of that have to be overcome. So I decided to pick the early probes of the early universe and the small-scale dissipation as one of the things that I want to explain a little bit more in terms of the physics. I decided to not talk about the late universe, the Y distortion and the relativistic correction. They help you learn about structures in the universe. And then I will also talk about things like the arc excess and the Hubble tension and the recombination lines a little bit as the last part of my, I guess, 15 minutes nominal. So 5 minutes each, let's see. Right, so why is the early universe so interesting? Well, first of all, of course, we understand we want to learn about inflation. And if we were accessing new signals like the B modes, or if we were accessing other scales like small scale universe, we would be probing basically aspects of our early universe and the initial primordial fluctuations at different scales. Spectral distortions, as I will explain you, will allow these kind of things. But I want to highlight here, we have seen this amazing, change in our capabilities with the first detection of gravitational waves, right? These mergers. And one of the big questions, which was immediately raised there, was this a detection of primordial black holes, right? And of course, this discussion is ongoing, and I think we all agree that probably primordial black holes are not making up all the dark matter, but they could certainly play a role in our cosmological model, maybe as seeds for the supermassive black holes that we see, maybe just as part of the typical budget of the energy density of the baryonic sector that then transforms into dark sector, essentially. So that's one thing that tells us that something might be going on in the early universe at small scales, right? Because lambda CDM wouldn't produce any black holes. but we might have these primordial black holes, right? And then we have, this is a more concrete version of constraining the existence of primordial black holes and their contribution to the budget of dark matter. So, here are various constraints. Here are some on the larger, masses. So the so-called intermediate mass black holes, 10 to the 3 solar masses, and so on. And here the more microscopic, solar, subsolar, and planet and moon-like black holes. So this is a typical thing. And as I said, we can rule out probably that black holes, at least with a monoenergetic or mono mass function, can be just all of the dark matter. But people like Günther Hasinger and gravitational wave community, they are talking about populations of black holes, which could be, all kind of curves in here, and you can actually make still up a significant fraction of the total energy density of the dark matter in black holes. And they behave basically once they are formed as collisionless particles. So this is actually really interesting, right? And then there's also the great, discovery of this stochastic gravitational wave background. And some of the explanations could be that these are sourced by small-scale density perturbations. So here's actually a figure that was taken from this EPTA paper, which I was very happy about, because they showed the constraint they would be putting, or the kind of requirements that they would be having on the amplitude of fluctuations at different scales. So these are very small scales, and they would be requiring fluctuations here at these scales to explain their gravitational wave background, their stochastic background. And Firas has already excluded this part. Yeah, so I was really happy that they actually featured the constraints on this kind of models from Firas itself. And here's some models that could in principle do it. And I can tell you that Firas is not short of actually excluding these models when you take the total integrals. So anyway, the interesting thing is there's a complementarity here between things that we have been seeing, like the gravitational waves from mergers of black holes, like these stochastic backgrounds, and the small-scale universe. So this is really exciting. And I was at this meeting, the EPTA meeting in Sesto last year, where discussions were about what is the vanilla solution for their gravitational wave background. And one of the vanilla solutions is supermassive black hole mergers. Yeah, that sounds great, because we know they are in every galaxy, and they could in principle be producing it. The shape is not really quite right, all these kind of things, but these are already details. But there is a glaring problem. We don't even know how these supermassive black holes formed in our galaxies. So the real model for seeding them is not clear. And it could well be that there is some early seeds, that there is some requirements of early seeds, for example, and or just different lambda CDM evolution process that leads to them. So there is actually a problem. Even with the vanilla, you're not making up a new thing. With the vanilla solution, we don't know how that vanilla solution came into place. And again, the questions about answering this, that's where spectral distortions will come in and really help. Here I'm enumerating some other things like phase transitions and cosmic, there's cosmic strings and other things that people have been using. But vanilla solution, the important thing is that to really distinguish this, we need to understand, in complementary ways. And spectral distortions are one of the ways to learn in addition about this. So let me try to explain to you why that is. So here is a figure that is taken from a paper by Bryce Sear, one of my former postdocs, who is now at MIT, summarizing the power spectrum constraints we have at various scales, the current power spectrum constraints. So the amplitude of scalar fluctuations, basically density fluctuations in the early universe, as sourced by the early universe model. I'm carefully saying not inflation, because slow roll inflation would predict, given that we know from CMB anisotropies that the fluctuations can't be that large, CMB anisotropies would predict the amplitude of fluctuations to be this way, yeah, all the way there, just a quasi-scale invariant, slightly red tilted power spectrum from primordial, from slow roll inflation. However, the real observations are only solid here. In this part, we in principle have everything way open. Yeah, there's way more space we should talk about. Yeah, if you want to form primordial black holes, you need to go to amplitudes of, of order 10% or just sub 10%. That would, at least in the limit of Gaussian fluctuations, allow you horizon scale collapse to a primordial black hole. And because we haven't seen black holes, primordial black holes at certain levels, that puts already constraints on that amplitude in some way, yeah, with various contributions. So this is another thing, but it's, as you see, this is like at least 6, 7 orders of magnitudes away from the limit of lambda CDM, yeah, probably even 8 in the small scales. Things like the pulsar timing, SKA, LISA, they will promise to look at scales, let's say 10 to the 5 to whatever smaller scales, and constrain the amplitude of fluctuations, which will then constrain things like primordial black hole formation of stellar mass black holes, primordial black hole formation of even smaller mass black holes, and other aspects that could lead to, gravitational waves and so on. Spectral distortions from FIRAS already now exclude all this parameter space. Yeah, they put essentially the amplitude of the fluctuations at these scales of 1,000 inverse megaparsecs, 10,000 inverse megaparsecs. These are very small scale fluctuations. Puts them to a level that is, at the level of 10 to the -5. And that already excludes supermassive black hole formation just from the primordial universe. In reality, FIRAS 30 years ago, it could have been interpreted as like, there's no way to form supermassive black holes by primordial density fluctuations collapsing directly. That's what FIRAS already did 30 years ago. And there was actually disputes about this. What happens if you add non-Gaussianity to the problem? In reality, this is also still, it's valid. The statement is valid. Supermassive black hole formation by direct collapse is not allowed. So primordial the supermassive black holes we see are not primordial supermassive black holes. They might be seed black holes from intermediate masses or maybe even stellar masses, and spectral distortion measurements will put constraints on these kind of scales directly, but also indirectly, because in a cosmological scenario, you can't just jump from this level to this level in arbitrary sharpness. Actually, when you use slow roll paradigm, you can only go maximally, there's a certain maximal scaling you can have, and that means that you will be learning about with spectral distortions, even the smaller scale universe, you will be able to treat and exclude things. So spectral distortions, mu distortions, are the most primordial measurement you can do to actually constrain these small scale fluctuations when the universe actually is largely basically still linear even, right? At least in this regime, everything is linear, yeah? So this is really exciting, and the key reason why ESA has recognized spectral distortions as a unique probe of the early universe. But this picture is really rich, so let me go on and explain this a little bit more. I wanted to say a few slides, well, maybe I will skip this. If you want to understand the physics of how these distortions are created, it's basically just taking two temperatures, black bodies of two temperatures in a box, and shaking the box, mixing the black body spectra, you don't get a black body spectrum. The sum of two black bodies is not a black body again. That's the simplest way of saying, when you take these different temperature patches in the universe at small scales and you take Thomson scattering, just mixing them by diffusion, you don't get a black body, and then that leads to a Y distortion, which then thermalizes and gives you a mu distortion. But you will not get a black body spectrum out of that mixing process. That's the origin of the physics, and I'm happy to explain that more. Great. So this means that a spectrometer is really crucial for learning about the formation processes of black holes and the small scale universe. And the lambda CDM prediction is even reachable with even if we have no surprises at small scales, we would be seeing the mu distortion of 2 × 10⁻⁸ that is guaranteed from this signal, which Pixie will actually be able to see. Fossil is designed to see it at a level of 4 sigma. It's a challenging measurement. The signal is actually larger than the sensitivity of the experiment, but there's foregone challenges which make it much harder to get it. Yeah. Okay, so this is really a great aspect of spectral distortion science, but there's also a secondary thing. Just like scalar modes, here's for those that are a bit more theory oriented, here's just the transfer function of a K mode of 10 inverse megaparsecs. And you know that when these modes enter the horizon, and then start oscillating, the acoustic modes, they then hit the silk damping scale and then just dissipate away. That's the way you get the sourcing of spectral distortions. And tensor modes have exactly the same kind of behavior. If you have actually gravitational waves, yeah, then you source perturbations in the photon fluid, which also oscillate and then damp away when they hit the free streaming and damping scales. And that leads to dissipation of acoustic modes sourced by tensors, which means you can also put direct constraints on the amplitude of tensor modes. So this is really interesting, as highlighted in a paper that I wrote together with Tom Kite and Andrea Raveni and Subodh Patil, where we basically wanted to point out that this nice paper by Capetti and Komatsu and folks, which was highlighting that the tensor power here in this omega gravitational wave versus frequency, that the complementarity of these were highlighted. So Lightbird will measure at large scales at low frequencies, and these other experiments will constrain the amplitude of tensor modes at much higher frequency. And there is a gap here, which can actually be bridged by spectral distortion measurements. So spectral distortions have a sensitivity to actually constrain the amplitude of these tensor modes. Unfortunately, the constraints are not extremely strong because tensor modes, as we all know, they just go through the universe without losing any energy. That means you can't really source much distortions, but there's a tiny fraction of distortion sourcing. That means you get a distortion constraint. So this is interesting, and it's a way to constrain this gap that nobody else can do. Okay, and in fact, this is really interesting because you can also have the so-called scalar-induced gravitational waves, and I'm really running out of time. Essentially, when you have density perturbations at second order, you source tensor modes, and that can be constrained as well with spectral distortions, but I'm going to skip that in detail. Okay, so I want to use 1 minute on the arcade excess and then 3 minutes on the recombination lines. So let's see how that goes. The arcade excess is an excess emission that looks like a monopole on the sky at low frequencies. It was first pointed out by measurements here with the arcade balloon in 2011, but in the meantime, at 2018, Dowell and Taylor with LWA, a radio observatory, have actually confirmed this, excess being there. So the important thing is it's really isotropic on the sky. It looks like you can't model it with standard, cumulative flux of radio galaxies. You actually are falling a factor of 5 short on those. So this is a puzzle that we don't know. There's no real explanation. And what if this is, for example, coming from early radioactivity from galaxies? And, something that JWST was recently measuring comes to mind, little red dots, just showing that there's early activity. Again, that is all just, I'm trying to stress here that the small scale universe, the early universe, the onset of structures, supermassive black holes forming, all that points towards one thing, that there's something interesting going on at the small scales and in the early universe, which is not the standard extrapolation from lambda CDM, which we have constrained very well with large scales. And I'm even saying large scales, 1 inverse megaparsecs, Lyman alpha, and all this. I'm putting that into the large scale universe because it's pretty large scale still, right? So small scale universe holds surprises, and we see indications. The arcade excess is an indication. One can explain the arcade excess with some cosmic string models. I don't want to go into the details, but we did some work with Bryce Sear again and Sandeep Acharya, basically highlighting that when you properly thermalize the emission that superconducting cosmic strings produce by networks of strings produce, that you can actually explain the arcade excess without violating any of the other constraints. And one of the cool things is that this predicts signals even in the spectrometer regimes, and things like TMS will be providing new measurements here that will actually potentially be able to constrain different models and rule them out. So this is really exciting, and I think one of the great activities that are going on here. And of course, there's a lot of synergy with BZoo and potentially even with the future spectrometer. Yeah. So the arcade excess is one, from my point of view, a tension in cosmology that we have actually not been labeling as a tension, because there is a problem there. And in the most recent tensions paper that Eleonora Di Valentino was leading, at least the arcade excess is also now part of this. So I think this is really interesting and needs to be answered. but it points towards the early universe is funny, is non-standard. And the last part is the Hubble tension, where, of course, Hubble tension, we know about the discrepancy between high redshift probes of the Hubble expansion rate and low redshift probes. And one of the cool things is that the recombination lines allow you to actually assess some of the physics that we don't have any access to. So here's the recombination spectrum, and I can show you the slightly better picture, just showing you the individual contributions. We can calculate these contributions really accurately now. It's a small distortion, but it contains a lot of information about the dynamics of the recombination process and about the things that are happening at redshift 1000, essentially, which is one of the key ingredients in the analysis of CMB data, is the recombination history. So we have a probe of the recombination history in principle with the recombination lines. And we can calculate these recombination lines now, varying parameters, just like in the good old days of CMB anisotropies, where you had, CMB fast. You were really happy that you could finally, see how things depend and do the analysis. We can do the same with spectral distortions now. And that means we can constrain parameters, but we can also constrain physics that is happening in these different eras of the recombination. So the helium doubly ionized helium happens at redshift 6000, singly ionized helium at redshift 2000, and then the hydrogen recombination lines are just before the last scattering surface, where the CMB anisotropies become visible. The recombination lines are coming from redshift 1400. So if something funny happens in these eras, you will see traces of that in the recombination lines. And I'm going to skip this about the annihilation processes, but here's an example. We actually just did the following thing. We varied, we said, if there's early dark energy, how do the recombination lines look? If there's varying electron mass, how do the recombination lines look? If there's varying fundamental constant, like the fine structure constant, how do the recombination lines look? And you see there's differences, which means you can actually constrain these different physics with recombination lines. Now, the problem is the recombination lines are really hard to measure. They have many features, but you need a very high sensitivity measurement, which is basically the L-class version of things that we're hoping to do in the future, the real ultimate spectrometer mission. This would be really giving us direct access to these kind of questions. And I think with that, I'm going to stop and not dwell on it much more in terms of like the physics of the recombination, but the recombination lines are a way to probe directly the universe at redshift 1000 and non-standard things that could happen, which is, I think, really exciting. I had added this for Jorge for dark photon and axion conversion processes, but I don't have time now to go into the details. But we should have a chat if you like. We have now redone those constraints on dark photons and axion conversion processes, and Virus is in some cases still the best you can do for certain masses of dark photons and so on. So this is really interesting, and I will just wrap up here now. So I hope I convinced you that spectral distortions have a lot of physics and a lot of interesting aspects to them. We are now at the stage where we can definitely it's always difficult to say easily improve the limits of Virus, but I think it is actually a valid statement. I'm not stretching. If we would be spending the money, we can easily improve the Virus limits by factors of 100 for sure. Factors of 1000 is already a bit more challenging, at least in terms of budgetary constraints. But we are basically with Fossil able to dream about factor of 1000 improvement of a Virus, and that opens a lot of standard physics exploration as well as non-standard physics exploration, which I think is super exciting. I didn't have time to talk about the synergy with 21 centimeter, but I alluded to the arcade excess. Indeed, if there is an arcade excess created at early times, that will change the dynamics of 21 centimeter evolution, and you need to really do the full co-evolution of spectral distortions and 21 centimeter cosmology. This is in a paper by Sandeep Acharya and Bryce Sear and I. We have highlighted some of these aspects. And then there's also, of course, generally for a spectrometer, a lot of synergies measuring the late structure formation. That's exciting for many people. There's also the possibilities to constrain line monopoles, like the line intensity mapping people. They depend on lots of modeling aspects, and we can learn something about those models with the average sky signal. We can learn about galactic dust. We can learn about synchrotron. A lot of things can be learned with the spectrometer. So it's really exciting. Again, a paper that we have highlighted, and we can, in synergy with other experiments like LIGHTBIRD, the SKA, Simon's Observatory, CMB 4, and all these things that we are dreaming of doing and that are happening, we can do real spectral distortion anisotropy science as well, which I didn't have time to talk about, but there is essentially signals that can be created that are mu-T correlated signals and mu-Y and YT correlated signals, even with the polarization. And you can learn about the primordial universe from this, which I think is extremely exciting. And I want to really finish with this slide, where I just summarize again the fact that we are, excited about spectral distortions as a probe of the early universe is because of the ability to reach scales with, here is for fossil, to constrain the amplitude of perturbations, scalar perturbations, at scales that we don't have any other access to. And this will shed light on formation processes and all of these kind of things that I have mentioned. Questions that will answer these things are potentially linked to precisely the physics of this small-scale universe, which I think is extremely exciting. And we are missing out if we don't push this now, because in 10 years from now and in 20 years from now, well, these experiments and the ongoing things with gravitational waves, they will have learned several things, but they will have not accessed crucial information here at the slightly larger scales, which I think we should be complementing as a community. So this is really exciting. And I will stop there and then thank you.
Okay, so we have time for a few questions.
I was wondering about the instrumental challenges, right? What prevented FIRES from going even deeper? And is it the intercalibration of the channels of your spectrometer, the limiting factor in experiments like TMS, right?
Yeah, so FIRES was not photon noise limited. It was actually phonon noise limited. So it was basically not a low enough temperature. The detectors were not really reaching their photon noise limit. That's one crucial thing. We can easily, with cryogenics, which is one of the challenges of flying a space mission, because cryogenics in space is a challenge. Everybody will nowadays put that as a very high risk aspect. We can reach the photon noise limit now. And then the other thing is FIRES was not symmetrized maximally. So PIXI, or the fossil concept for that matter, PIXI is basically the strawman version of this concept. I should have put a slide maybe explaining it a little bit. It has two apertures where you have one aperture on the sky and the other one is covered by a calibrator. But then the cool thing is you can switch the calibrator to the other aperture and look with the other aperture on the sky. And in that way, you can fully symmetrize away the instrument, because you have the full symmetry between the photon path that you're taking. And that is one thing that allows you to kill many systematics that were hampering FIRES as well. So those are the... and then, of course, observing time is something you can change and increase the aperture size of FIRES. In fact, FIRES was, I think, similar aperture, individual aperture, like a 55, I think, centimeter aperture. So those things have not actually changed so much. So it's mainly these control of systematics, symmetrization, and photon noise limited detectors and optimization. And then, of course, one of the real things that is also important, we now understand the theory of spectral distortions so much better. We can actually say what kind of distribution of channels we need. What is the real, setups that we need, and how do we do this? I think and what do we learn most crucially? That has changed a lot, and I think one of the reasons why FIRES was 30 years ago and hasn't been followed up in a very significant way is precisely because we have not really seen the theoretical potential in this field, which we are now, I think, very aware of. Yeah.
More questions?
Thank you, Jens. Beautiful talk. So I was also wondering, in forecasts like the ones that you are presenting in this plot, are you considering foregrounds or just instrument sensitivity?
No, the forecasts are including foreground marginalization, but of course, there's a lot more. It's very similar to the B-mode foreground marginalization in many ways. We're using models of that we're also using in the anisotropy related anisotropy studies. And there could be, of course, big surprises. So we're trying to design the experiment in such a way that we are most prone to everything that we know, and we even include some averaging effects that are making things more complex in some of these analyses. But we will ultimately need a full combination of all existing data sets, potentially even anisotropy data sets, to really get to all these sensitivities and potentially even drill a little bit deeper. So we're still remaining fairly conservative in our estimate. It could potentially be better if we had an even better way of cleaning foregrounds by combining with different experiments and so on. So there is, I think, a lot of potential. I'm imagining that in 20 years from now, we will be able to strip away the low redshift universe and all the signals from the low redshift universe, and then we're just left with the primordial mu distortion. That would be great. Maybe 20 years is a little optimistic, but it's we are having so many data sets coming now, and the synergistic approach to data analysis. We have not explored the full potential of that for spectral distortion research, right? We're doing it in a conservative, very, very similar to anisotropy forecasts way, right? So there is potentially more.
Okay. No.
Yeah.
It is? Okay, now it is. How do, because you mentioned briefly scalar-induced gravitational waves, so how do they cause spectral distortions, and are they different from those generated by the primordial gravitational waves? So can you tell them apart?
It almost looks like I asked you to ask that question because I didn't have time to go into details. So this was the figure that I skipped, but it shows this aspect. So tensor modes directly produce spectral distortions. This is these lines here that I showed in the other figure as well. That was just like tensors. They shake the medium gets the quadrupolar anisotropies, and they source photon perturbations that then dissipate like silk damping, just the standard Thomson scattering effects. That's one way. That's the direct way. That gives you this, and you see there's even existing limits. All the existing limits on scalar perturbations would give you this here. I will explain that in a second, but there's even regimes where these future measurements could in principle directly constrain the amplitude of tensors. But the scalar-induced are working the other way. Scalar perturbations at second order produce tensor modes. And those tensor modes, they would of course dissipate, but that dissipation would be very small and we wouldn't see a spectral distortion. But if there's scalar perturbations that dissipate, that lead at second order to tensor perturbations, then that's only a fraction of the energy. The other fraction goes into spectral distortions directly by scalar perturbations. The scalar perturbations leading order are dissipated by scalar fluctuation evolution. And at second order only they created the tensor modes. So you actually can directly ask the question, what is the amplitude of the scalar perturbations that are allowed? And that gives you this line when you just take all the constraints we have on scalar perturbations. And there's one really crucial thing that LightBird could in principle, using existing limits on the scalar perturbations that we have, in particular those from Firas only, could still be seeing scalar-induced gravitational waves that would be in excess of their sensitivity, which means if they can't really determine the scale dependence of these signals, they will basically have a detection of R if there's amplitude fluctuations that are consistent with Firas. If you would be having Pixie or Fossil, you can exclude that. This is a really interesting synergy. And it just comes from the fact that you can directly constrain scalar modes with spectral distortions. And the secondary signal is a small one, which is the gravitational waves that then are here. But that can still lead to a significant amplitude fluctuation. Yeah.
Thank you.
Changing gears, Jens, just a silly question. I was a bit surprised about the arcade. Can you go back to this slide where you were showing the arcade excess and the confirmation at lower frequencies?
Yes.
I wasn't aware of this. This was from radio, this one, right? So
yes.
The leftmost points, these are radio experiments, you said?
Yes, LWA.
LWA. So are they just basking all point sources? So they are sure that this excess is not corresponding to any population.
So they are looking for the isotropic contribution essentially, and they are saying that this isotropic contribution is consistent with the extrapolation that you would get from the what you had done, what was done for the arcade excess. And then you can ask the question, what's the source? They don't resolve it, but you can then ask the question, well, if I have resolved, if I take all my resolved radio galaxies and stack them, or I even do population synthesis with models, I fall still a factor of 5 short of this signal. So
5 short of that signal. Yeah. Okay.
This signal is in excess of what you expect from any modeling, or even synchrotron emission from our galaxy can't explain it.
So at least 80% of the signal, you say, at least it's a factor of 5 of any prediction. And the slope? Is it close to?
That's very synchrotron-like. So that's suspicious. That tells you it is probably just some radio populations,
Right.
but early, potentially very in dense environments where you don't get as much high energy outputs because it's just reprocessed and you get everything in radio. So what I'm suspecting could be interesting, and Alberto, we have been discussing this, is that we have just earlier onset of activity in the early universe, and this activity is coming, is very, very loud. And that's maybe how we can explain the Arcade excess. And that's how we maybe can even say why supermassive black holes didn't have as short time to grow. They have maybe earlier time because things set on way earlier than we think in Landers-Lien. And it would be leading to things like the Hubble tension, with clumping of the universe being one of the versions of, changing the recombination process. So it's really all, for me, it looks like there's lots of things that are related here.
Okay, so I think it's already time. We thanks again, Jens, for the talk. I remind you that he will be here until July 7, so first corridor. So if you want to interact with him, please take the opportunity. Thanks.